we can try to arrange a meeting on Friday. All right, so today I think I kind of want to move on to the standard library, especially the part that deals with functions, function objects, and kind of run through because uh, uh, I probably should have maybe done some of these topics earlier, but now is as good a time as any. So let me begin by sharing. I have a bunch of source code and also some slides. Okay, so this is the plan. I don't think we'll complete everything we want today. So this is it should say plan for the topic, right? But next Tuesday, since Thursday there's no class, we'll probably complete the rest of it. And there's actually quite a lot since 2011, 14, 17, and then 20. They've been constantly adding more and more. So a lot of the interesting stuff that is going on in C++ is all related to templates. So uh, I think even a textbook with 2,000 pages is not enough to cover the material. It's just crazy. So we'll touch on many aspects related to templates, variadic templates, lambdas, generic lambdas, and all the other sort of like common stuff that we tend to use. We'll leave the sort of esoteric stuff away because if we don't use it, then there's no particular reason to spend our little time that we have. Okay, I'm going to start at the very beginning. Okay, I'm not going to start with function pointers. We have covered that. But the main thing that you need to understand is that anything that behaves like a function can be thought of as a function. Okay, and the one particular thing that we know that looks like a function is the regular C style or C++ style function. Okay, and we looked at function pointers that allow you to indirectly access these functions. So we're going to uh, continue on to function objects. So these have always existed in the language since the early days. So there's nothing new about them. Different people call them different things, functors, functionals. A lot of it is related to mathematics and the terminology from mathematics. So I just call them function objects. It's simple, right? Some people call them functors, but the whole thing sounds kind of weird, so I don't use it. What exactly is this? Well, the basic idea here is that you are overloading the function call operator in your class, okay? And what that means is that when you define a class X that you see here and overload the function call operator, then anytime you define an object of that particular type and you essentially can treat this particular object with the function call operator as though it is a function. And obviously what is happening is that in this particular case, func, which is an object of type X, is essentially invoking its member function, which is the function call uh, operator overload. And uh, after uh, uh, function objects, 2011 C++ introduced something called lambdas or closures. And it's the use of function objects is sort of reduced because we can write lambdas to kind of replicate much of the behavior in a much more convenient fashion. But I think it's still useful to kind of look at function objects. There are places where you may find them more useful, especially if you have to capture some, complex state, and also to understand how lambdas work, because we know class classes and class design well. And so those things called lambdas essentially become anonymous classes that overload the function call operator. So for you to be able to understand lambdas really well, and I presume if you continue with C++, lambdas will only become more and more complex as the language evolves. It's good for you to kind of always trace back the implementation details to classes. So I think we'll spend a little bit of time on function objects and then move on to lambdas. Um, so the question many people have is, well, I know how to write functions and I know how to uh, define pointers to functions, and I can use these function pointers with my algorithms. I'm talking about the standard library algorithms such as countf, findf, accumulate, and so on and so forth. The basic idea here is that functions don't capture state, right? Unless you define static objects. But if you have a static variable inside a function, well, that particular static variable is going to be shared by the many invocations of that particular function. While with a function object, you can define as many objects as you wish, and each one of them will have its own unique state. So that's kind of what makes function objects more popular than function pointers. The other thing is that each function object has its own type. So we can actually specify these function objects as template parameters. And so it makes it far more convenient to pass around functions or function like things with your algorithms or anywhere else where you where you have template, where you tend to use templates. And generally, they could be a little bit faster than function pointers because function pointers are reconciled at runtime, while templates are template-based function objects, which are the more common ones, are generally, hopefully, resolved, possibly, I should say, resolved at compile time. And if that's the case, then they turn out to be more efficient. Of course, they're going to cost you more in compile time, but what that means is that at runtime, you tend to get those benefits or efficiencies. So here's a kind of like I put some of the source code which I'll upload uh, because typing up some of the source code may take way longer than we have time. So I'm going to just show you where these functions, and then you can look at them later on at home. So what was the name? So this is our very first function object, W something. So there's a lot of boilerplate stuff. And here's the first example in terms of why function objects. Let's say you want to write, if you need to add the value 10. Why 10? It's something interesting in your particular application. And you need to add this value to every single element of some container. Okay. And what you do is you author this particular function. Can you guys see my code?
Yep.
So you basically author this function, and by now all of you understand what is the problem with this particular style of programming. Well, you're hard coding these values, and if the application requires a value 20 to be added, well, you got to go back and either replace 10 with 20 or write a brand new function. And all of that is quite annoying, right? And you can see me here, for example, use the for each algorithm. The for each is one of the most versatile algorithms. Uh, Generally speaking, when you have a collection of things, we need an algorithm that goes and touches each one of these things to do something specific, right? And what we are doing here is we are making this particular function be invoked on every single element of the container that you see here. So one, essentially, because we are passing each one of the elements of the container by reference, we are essentially converting each one of these to be 11, 12, and so on, right? And so this is something that works, but the problem is maintenance. This is not very convenient in terms of maintaining. Well, some of you might say, well, maintenance is an issue. Then obviously I can write a function template and use a non-type template parameter. So in this case, we can create an infinite number of functions based on the type of or the value that you wish to add. So this is the non-type template parameter. So hopefully today will also be a sort of like a review for you guys in terms of function templates. If there are any specific questions, let me know. We're not doing anything that we wasn't done in 10 HLP2. So this is easy enough to use and generalizes from using the value 10 to whatever we want. And here's a use case, right? So essentially, I can create an infinite number of functions at compile time and specify what is the exact value that I wish to add. In this case, I want to add 10, so I instantiate a specific function that allows me to do exactly that. So you have seen, this style of programming in HLP2. The other thing you can do is you can define a pointer to a function that is of this particular type. And that is exactly what I've done. Just to show you that, yeah, using these function templates, I can define a pointer to a specific instantiation. Remember, PF is a pointer to a function that essentially hard codes this value 11 with this signature. And so this is pretty convenient. Now I'm adding 11 to these values, which already were incremented by 10. But we have this idea of a function object that essentially does what we did earlier, but in a slightly more advantageous way. And we'll talk about the advantages in a moment. So what we're doing here is we are defining a class called add value. And this particular function really contains two functions. One is some sort of a constructor to initialize a specific instantiation of this particular object. And the second one that you see here is the overload of the function call operator, right? And I'm using no except liberally, obviously, because I wish for some speed gains because I don't want any sort of exception mechanisms to be implemented. So this particular function is going to allow me to essentially invoke any object of this particular type with the function call. So anything that looks like a function call, anything that looks like a function is a function, right? That is how C++ treats function objects. But it's a class-based object that simply overloads the function call operator. What makes this different and better than these ordinary functions? Yeah, some of them are templated and others are not, simply because in this particular class-based object, obviously I can retain state, right? I can have all kinds of additional data members if I so wish, and essentially be able to do more complex things than would be possible with this particular, type of function or a pointer to a function of this particular type, because that's exactly what's going on. Here we are instantiating a specific instance of this particular function where value is going to be hard coded to 10. And this particular syntax is going to declare or define essentially a pointer to that particular function that we instantiated. We're not really calling this function here, right? We are simply gathering the address of this particular function that we ask for it to be instantiated, and we pass that address by value to the algorithm. That particular function, our algorithm is going to take a copy of that particular pointer and invoke that function through that pointer. And the for each, as we'll soon find out, is sort of unique among all the algorithms. It actually returns a copy of that pointer that we passed it, right? And we'll see how that can be useful to us. No other algorithm does that except for each. So anyways, there are three things we saw. One is a plain old function. And here we are declaring a pointer to that function. Then we have a template version of that same function where we use a non-type parameter, template parameter. And we are instantiating specific instances of that function and getting pointers and passing them again to similar algorithms. And here we have uh, a class-based object that overloads the function call operator. And we call this a function object because objects of this particular type, when they call, when they use the function call operator, essentially for all practical purposes, it looks like a call to this particular function. And what I'm doing here, this syntax, make sure you understand this. We are defining a temporary unnamed object of this particular type. And that particular object is being instantiated. It requires a constructor, right? Otherwise, there's no other way to instantiate an object of that type. And we are instantiating that object that has no name, and we are passing that object by value to this algorithm. And generally speaking, that's exactly how function objects are passed to algorithms, always by value, right? You could, if you want, pass them by reference, but the syntax is so unwieldy that we don't generally tend to use it. So if you run it, let's just run it just to make sure before I put it online that all of this works. You will see all the different invocations. And we started with 1, 2, 3, 4, 5. So we are able to kind of add specific values, and there are all these different invocations, right? One through plain old functions, one through pointers to instances of function templates, and 3 through function objects. So are there any questions about this particular overload? I have one question for you guys. Do I need this? Or do I not need this? Is it something that if you were writing your own class, would you make this be const? Should you make it be const? Obviously it's working for me, but is it good design or is it bad design? It could be a true false question, right? How would you design your class? Should it be const or should it be non-const, or it doesn't really matter? And obviously this is my favorite, none of the listed answers. So we have 4 answers.
I think it doesn't really matter in this case.
Well, in this case, but you are creating it for use forever, right? So we have to think about all the different clients who may want to use your, your class forever once you create it. Every time somebody needs something, then you have to go in and touch this particular definition. It's only going to lead to maintenance issues. The simple answer is, guys, anytime you write stuff, the default, I'm pretty sure I explained this, the default should be const. Then you decide, you argue for why it shouldn't be const, not the other way around. Why should it be const? Well, if it wasn't const, then some of your clients might decide, hey, I would like to create an object, right, that is read only add value, and then I would like to use it with a particular algorithm. And notice, once we initialize, where is the class? Once we initialize value, we don't actually ever change the 4 bytes associated with an object of this particular type. So technically, it should be const, but I'm giving you an example where we don't make it be a const. And I say, okay, let's go ahead and pass an object of this particular type, right? And see what happens. Okay, it worked because you're passing by value, so top level constness goes away. So let me see. So I need to pass by reference. So I might create another use case that looks like this. And I say, okay, I want X to be incremented by 10, right? So this behaves like a function call. So the reason why this worked is because as we call this is a top level constness. Since we are passing by value, nobody cares whether this is a const object or not, because the compiler is instantiating a copy of this object. And so my example was a poor one. But my mind is sharp enough to come up with this example. And in this example, what I'm doing is I would like to make a call to that function call operator that we overloaded in this particular class. And I would like to do it like this. And after I do this, technically, my X should be incremented by 10 to become 21. So let's see. And obviously, it's not going to compile simply because this is a const object and the function is not const. So to everybody who was thinking that the const doesn't really matter, what you're doing is you're reducing your clientele, or how many people can essentially use that particular function. So now you put that back and it's going to work, right? And obviously X is going to be updated to 21. So anyways, this is a much more simpler application of the function call overload. And these examples are the more useful ones, because what we are doing is we are passing this particular object which overloads this operator to the algorithm, which is then going to go ahead and apply the function call overload and supply each one of these values in turn. So the for each iterates through the entire collection, and for each element, it's going to invoke this particular function, right? So it kind of looks like this. RAV, let's say, if I have a pointer to each one of the elements of the array for a specific array, then this is what I'm doing. I'm invoking this particular function for each one of the elements that this iterator will successively point to. Okay. Anyways, so folks, make sure you don't lose points. Okay. Anytime you don't see the const, then be suspicious. There's something shady going on. All right. Any other questions? Function object. So quite straightforward because all of you are pretty good at overloading functions or overloading operators. So this is just overloading a function call operator. Okay, I kind of think of breaking up function objects into all these different kinds. It's good for you to know them. Sometimes they have these names. I call the ones that have 0 parameters as generators. Right, and what they do is their only purpose is to sort of create sequences. Then you have the single parameter functions that are called unary functions, and the predicate versions are called unary predicates. Then obviously we have the binary, and there's a whole collection of them in the standard library, so we'll kind of briefly look at that. And finally, predicates are stateless function objects. Okay, what does stateless mean? Stateless is essentially they don't retain any state. They are like pure functions. A pure function is a function that doesn't really change. Any uh, sort of like it doesn't have any side effects, right? Anything that writes to standard output, for example, is updating a buffer somewhere, while a pure function never ever has any mechanism that allows it to change certain state associated with that function. Similarly, a function object that doesn't have any specific state associated with it that changes every time it is called stateless. So a predicate is a stateless function object that returns a true or false value. So we'll look at some examples of that. Actually, I have them listed here, so I'll quickly go through these source files just to show you what that looks like. Okay, so this is a typical case of uh, uh, a, a a sort of like a uh, overload that takes 0 parameters, as you can see here, and I think of it as a sequence generator. And the idea here is that I have a constructor and that allows me to initialize a data member, and every invocation of the function call is going to increment for that particular object its data member. So it allows us to generate values in sequence. Obviously, you can generate numbers in any particular sequence that you want. There are random number generators that sort of look very similar to this. It's not very difficult to build those. All they do is they rely on some, uh, uh, you know, uh, random number functions that are implemented as part of modern C++. And by making repeated calls to those functions, they can generate random numbers for you. All right. You can always generate only odd numbers, prime numbers, all kinds of numbers. So this is quite commonly used in lots of applications. So that's why I kind of decided that everybody needs to know about a function object that takes 0 parameters. It kind of looks like this. And we tend to use it like this. So generate is a library function that essentially allows us to fill the contents of some container with the values that are returned by this particular generator, one in sequence, right? So the first guy in this particular container numbers is going to be incremented with 5, the next one with 6, the next one with 7, and so on and so forth. And obviously, the number of values that are generated is simply governed here by the size of the array. All right. Uh, and if you want to be more specific, then we have a version of the algorithm called generate n, which obviously fills you supply the number of values that you wish to generate. So notice that I have defined two specific objects. Okay, each one of them is different. This is a temporary object that gets created and obviously goes away. And then I create another object where the starting value is going to be 9. So what sort of logic you put in to this overload is going to determine what sort of generator you have. So it's quite common if you want to say create particle systems, what have you, and you want them to kind of be built using some certain values that you specify, then it's easy enough to fill containers with these values as efficiently as you can. And also notice that in this particular case, Li has 0 elements, so I use a iterator adapter that essentially does a allocation that does a pushback essentially, right? And makes a copy of the value that we specify. And the other thing, we'll talk more about this as time goes by. I just thought I'll introduce this. This is a specifier that came about in 2017. And basically the idea is that apparently I myself don't do these things, but I suppose others can. Sometimes you are calling a function and that particular function returns a value. Somewhere in your code, you decide that you don't want to make an assignment, right? From the value returned by that particular function. And apparently, it's the cause of bugs. And this can happen in many different circumstances. You can do this for classes, you can do this for enumeration types, but here we are doing it for a function type, and we are asking the compiler to issue a warning if the value that is returned by call to this function is not being assigned to, right? And in other words, I'm making a wasted call, a no op. And uh, the purpose of this specifier is to essentially warn you against such I don't know, misuse of a function that returns a value. So that's really all there is. There are more details. I'll talk about them as time goes by. For now, the important thing is that if you don't make use of this particular value, the compiler will complain, right? For example, for example, let's first compile this just to see if it works. Sorry, guys. All right. So anyways, it works. What I'm going to do here is define an object of this particular type. And I suppose it takes a initializer, let's say 5, and then I make a call, right, to the overloaded function call operator. So the compiler should flag a warning. So notice that it's not an error, it simply is a warning. And since obviously we put the warning for making sure that all warnings are converted to errors, you can see here that, hopefully maybe it'll give you some hints as to why maybe your code is not working because you're ignoring the return value. So that's something that came about in 2017. And if you have good habits, sometimes these sorts of type specifiers seem like C++ is going overboard, but at the same time, they also want to make sure that a lot of the secure software that is being written in C++, for missile systems, aircraft control systems, nuclear power plants, all that stuff is as robust and fault tolerant as possible. And so probably we need to kind of, you know, simply start being learning about these things and using them, even though you yourself may be very disciplined. Okay, any questions about the sort of frequency, not frequency, the generator? Okay, if there are no questions, then let me quickly show you examples of the unary function object, binary, and then we'll go to the predicate. So unary. All right, so what am I doing here? So I'm going to continue using my generator. Uh, and so today I consciously I'm using no discard so that it becomes familiar to you guys. And I think there are so many new things that the best thing to do is kind of jump into them and start using them. And notice a simple function now looks quite complicated with a lot of qualifiers, right? And in the olden days, we probably wouldn't have had these two qualifiers and this qualifier, and we would have had the const, everything else not necessary. But now we are sending signals to the compiler. So guys, this is my example of a unary function, okay? And notice its job is very simple. Of course, you could write it as a function, but as I explained, function objects could potentially be a tiny bit faster than function pointers. And in the future, they can retain state. So they're more flexible. And they can be specified as uh, template parameters much more conveniently. So what do I have here? Pretty simple and straightforward. It is simply a function call overload that takes an integer value and simply returns this particular result. That's it. And of course, like anything else, you can, write a template so that it works for all integral types or potentially all numerical types. But here I've just kind of kept it simple because there's so many other things going on. I just wanted to keep my code to be as direct as possible. So not very complicated. And how do we use it? So notice I'm using my generator to fill my container with some values. And then I use the familiar transform algorithm, which basically iterates through each element of this container and applies this particular algorithm. And the return value is essentially, so what happens here with the transform is that if you have an iterator that points, while first is not equivalent to last, let's say, then first is a pointer to each one of the elements in our container. So the algorithm works like this. We have a function that has been supplied, and this function has been given the value that the iterator points to, which is the value stored in the current element. then the function goes obviously and returns a particular value, which is then used to write. That is the purpose of the transform. Except here we have, the destination is essentially the source. So we have essentially something that looks like this, dest. And then, every, excuse me, then the compiler will have some code that essentially makes the destination and the source adjust. I think you guys are pretty familiar with the transform algorithm. And notice, again, the syntax looks kind of weird. I'm not calling a function. I'm simply instantiating, because if you do this, right, this is not an object. This is a type. And the compiler will, depending on whether it's templated or not, give you horrible warnings. Hang on, it worked. Oh, I'm compiling. Okay, well, because it's not templated, it didn't give horrible warnings, but you can see that the message is quite cryptic. It says expected primary expression. And so if you are writing code, this is the most common mistake, right? Where you are using the type rather than, remember, passing a function object. You want an object of type class. What is it called? Two square to be passed to the algorithm. And so now it works. So this is obviously modern syntax. The old syntax used to look like this, and that was a little bit more confusing because it looked like this was a function. No, you are simply instantiating a default version of this particular object. So either works, but probably this one is more nicer. All right, so that is with that. Then let me show you a binary version. Again, I'm using the generator. I got the old stuff, and then I don't. I kind of my experience is that I don't write a whole lot of binary, uh, function objects, because there's a lot that is already supplied by the standard library. And here I have add. It actually is already implemented by the standard library in a header called functional, and we'll go take a look at that in a moment. And this is, a lot of the useful operators that we tend to apply and generally are binary. So we have multiply, division, addition, subtraction, and so on and so forth. And that is exactly what's going on here. I am essentially overloading a function call operator that takes two of these parameters. This is templated. The earlier ones were not, so this one I decided to template. And notice, if you are using a template, it's never a good idea to pass by value, because you are going to perform a copy. And if you have a big vector, then that could cost you, right? So it's better to lose on the tiny little things than lose on the really big one. So I would always recommend that you pass by reference. All right, so as you can see, not a whole lot going on, and the generate function is nice because I have a generator that allows me to fill values. I don't have to hard code them anymore. And uh, yeah, and using uh, the, where is the ad here, guys? Does anybody see the ad? Yeah, there, right? So I'm using the ad. Now I wanted to show you this particular piece of code is because in C++ 20, okay, they came up finally with something called an arraysf. People have been asking for this for decades now, but finally it is there. Why is it so important? Well, suppose you had the need to perform some filtering operations on your containers. And this particular container, for example, I have, this is called a binary, no, this is called a unary predicate. Obviously, this is a function object. And what it does is that it returns a true or false in contrast to all of the other function objects that we have seen. So the definition is somewhere here. This is the definition. It's pretty simple and straightforward, and it works for all, I suppose, numerical values. And what it does is this. Obviously, it doesn't do a good job with non-integral numbers, but assuming that we can invoke it only for numerical objects, what it does is that it simply takes the value, and notice it's got no state. It's not getting updated. None of the memory associated with it is changing. And all it does is that it takes a value, performs some operation, and it returns a true or a false. If the number is odd, it returns true, otherwise it returns false. And what we are interested in doing is we took this container, filled it with some values. We did some, manipulation with those numbers. So the container got further transformed. And then at a certain point of time, what I would like to do is remove all the values in that container that are odd. All right, it's a fairly common thing. It happens quite frequently. We initially have certain things in our container, and then at a later point of time, we want to remove certain containers. And we want, obviously, when we remove something, the ones that are retained to be packed together contiguously, right? If you take a vector and there are big gaps, that isn't going to be of any help. What we want is the ability to arrange contiguously all the numbers that are even. And it wasn't straightforward implementing this up until C++20. You had to do it in 2 steps, and think of it as the erase remove idiom. So make a note. Anybody talks about the erase remove idiom, well, this is one of those things that they talk about. And why is it important? Because I'm pretty sure, right, for if in the outside world where you go and work, if you're going to go work in a bank, wherever, and if they are using C++, it's going to be years before they get to the C++20 part, maybe by 2030, right? Because, just because there are new versions of the language doesn't mean everybody suddenly knows how to use that. So I presume many people are using C++11. And when you go there, this particular function is not something that you can use. Maybe for new software, but the old one, it still is going to be C++11. So this particular idiom essentially shows you how we need to remove elements from a container such as a vector. So how do we do that? Well, there is a standard algorithm called remove if, right? Remove if some condition is true. And that particular condition is nothing but our predicate. And we are iterating through all of these values and determining which ones are odd numbers and which ones are otherwise even. So this guy, what it does is that it rearranges, right? It's a pretty expensive thing, of course. It rearranges your vector so that it's now divided into 2 parts. All of the even values are at the head. All of the odd that need to be removed are at the end. But this guy doesn't actually do any removing. You have to call another function that is specific to the vector interface called arrays. What this guy though does is that it returns an iterator to the start of where all the odd numbers begin, right? So this guy did some hard work. It packed together in the front all the even values by shuffling them around, and then after the odd even numbers are done, all the odd numbers begin. But of course, you want to remove them because they serve no purpose. And this guy doesn't change the size requirements. So all you have done is you have completed the first step of the arrays remove, right? And so the way it works is that this guy returns an iterator to the start of the odd numbers, and you're calling the arrays algorithm. Okay, and you're specifying where the values need to be erased. So it would be from the where the odd numbers begin, and obviously since we are using half open ranges, it would be one pass. So make note, guys, if ever you need to kind of do something like this, then there is a way to do that. And in your games, if you're using C++20, well, there is the new thing. But if I myself, I'm going to ask any questions in the midterm, final, excuse me, the midterm is over. Essentially, we are referring to C++17. So 20, not yet. So anyways, I just thought I'll introduce that to you guys, right? It is quite an important idiom, quite useful. Okay, so what else do I have here? Yeah, so again, I defined another container of vectors, numbers 2, numbers 3, there are two of them. And then I filled some values in numbers 2. And then I essentially add. So notice now there are 4 iterators here. It transform, right? So transform is sort of got the ability to allow you to perform, functions. So f of f, the function applied on x and y. Well, the x values are going to come from this range. The y values are going to come in this range. The result of applying this function, which is really the add function, are going to go sit in, the third container. So transform is pretty versatile in that sense. And what this guy should do now is it should give you the values in numbers and numbers too. Let's, did we run the code? No. What's going on? Oh, I'm in binary. I'm sorry. So 4 plus 3 is 7, 0 plus 4 is 4. So you can see, that at the same time as we are looking at functions, we are also sort of exposing ourselves to algorithms. All right, any questions, folks? Okay, there are none. Then the last thing is predicate. I just want to see if there's anything useful there. I think we have seen this, right? Odd number. So there's nothing new here. All right, so let's move on. The big thing is that everything is done by value, guys. So it's quite important for you to understand that sequence is an object of this particular type. And what happens here is that since I'm passing by value, it's the copy of sequence that is being manipulated by this algorithm. And so when I make another call, obviously, this guy is going to generate values starting from 3 all the way through to 8, right? So we are passing by value. But sometimes you may want to get back the past value. And the reason why you want to do that is because maybe there's some state setup, right? Sorry? Is everything okay, guys? Any questions? Okay. If there are no questions, just turn your mic off. It's easier. Okay. So sometimes, some of these function objects may have certain state, and that could be quite useful for us to get back. For example, we have a big container, and that container contains integral values, and I want for example, you have a huge particle system and you want to know the average power, right? Something like that. And you want to get back after the function object has iterated over every single element. So none of the algorithms, as far as I'm aware, give you access to the copy, right? The value that the function object that they copy. So there are sort of like 3 ways. None of them are good. The first one is let your class essentially make references to global state. This is the worst possible idea I can ever come up with, so we'll dismiss it, right? The whole idea of using classes is, we want abstraction and data hiding and all that stuff. So changing global state and using global variables to transfer data, that's a silly idea. The other thing we can do is rather than take the default pass by value approach, we can pass by reference. So I'll show you how that works. I believe I have an example, but the syntax is so horrible that, generally speaking, it's so disgusting that nobody will want to ever use it. So the only other alternative is to use the for each algorithm. And that's why this algorithm is actually quite important in the entire list of algorithms that we have. So pass by reference, here's an example, okay? The syntax is horrible. So what am I doing? Remember, generate and all of the standard library algorithms are function templates. So they have certain template parameters. And if we look at some of the code that we had written earlier, well, we had what is called implicit instantiation. So the compiler, what it did was that it said, okay, you are interested in creating an instantiation of the generate and transform, whatever algorithm. So here I am going to look at your function arguments, and using those function arguments, I am going to deduce. Actually, using those function arguments and the function parameters, okay? I'm going to deduce the template parameter. So if all of this sounds confusing, you'll have to hang in there because next week, if we want to understand auto, decal type, all that stuff, we need to understand our template argument deduction. But basically, what I'm saying is this. We made calls to generate and all these algorithms. Where is it? Here, you can see. And what the compiler does is that it looks at these function arguments, 1, 2, 3, whatever. And then it deduces implicitly the template parameters and uses those template parameters to instantiate a specific version of the function template for us. If one already exists, then it's great. Otherwise, it instantiates one. This particular technique is called implicit instantiation. But you could, if you wanted to, instantiate things explicitly, and that is what I'm doing with this really ugly syntax. It goes all the way here. Nope. From this all the way up until here. Let me, yeah. So from here to here, what we are doing is we are specifying the template parameters explicitly. So I'm using a iterator adapter for my list. So notice that the compiler will look at this and basically determine that the type is this. Pretty complex, right? And you got to specify that. Then this guy is an int, so that makes sense. This is an object of this particular type. Normally we pass by value, but notice the implicit is now being explicitly specified to be a reference. So now when you pass by reference, whatever changes are being made, to this uh, uh, particular function object are going to be retained. And this guy is now going to contain the transformed version, right? So here I initialize with 3 and here I say I want 5 values to be generated. So I believe that would be 3, 4, 5, 6, 7, right? I think we have to look at the algorithm. I've forgotten. Or it could be, I'm not sure whether I'm pre-incrementing or post-incrementing, but with respect to the comment, it seems like I'm pre-incrementing. So 4, 5, 6, 7, 8 are 3, 4, 5, 6, 7. So 7 is incremented to 8. So I suppose it's post increment. So this guy has the value 8 updated in its state in its local data member. And so I'm retaining that state because I'm passing by reference. And that is quite ugly, as you can imagine, right? Trying to write code like that is not a pleasant task. So the only thing I think is a suitable solution is the for each, and we have a simple algorithm or a simple example that shows you some of the applications of the for each algorithm. So again, it's the only one that does this. So again, everything is the same except that I've created a class that contains quite a bit of state, right? Notice, not only does it have the overloaded operator, but I'm also defining 2 private data members. And the idea here is that they are going to be default initialized to 0 each. Now, what am I doing with this? Well, basically, I'm filling up this container with some values, and I'm using the for each algorithm essentially to perform some statistical analysis of the values that have been stored in this particular container. So what am I doing? Well, I'm telling the for each algorithm for every single element, right? Make a call to this particular function object. And what does that do? Well, that particular function object is going to receive the value stored in that particular element. And notice I'm not changing anything in terms of the container, but what I'm doing is I'm accumulating the number of elements that I've visited so far and the total sum of all of the values that have been visited so far. And when I'm done, the for each is the only algorithm that returns the copy that it made, right? So the updated function object is returned back to us with this new state that it has. And since copy construction is default, the is default specified. What happens is that M is going to become a copy of the object that got manipulated by the algorithm. And this guy will contain the average value. And how do I compute the average value? Notice that I have a function, part of the interface of this particular class, that simply takes the total number of, the total value divided by the total count of the values. And that gives me the average. So this is a good example of where potentially the for each has the ability of the for each algorithm to return the transformed function object could be of some use to a programmer. All right, so that's any questions, guys? Okay. So now we know how to do this. Okay, so let's not get into the mathematics associated with this. Lambdas are also called closures. The name comes from a particular topic in mathematics, so we won't be concerned with that. Obviously, the basic idea here is that I'm able to write functions that can be defined in line. In other words, I define a function at the place where it needs to be called, and once that particular function is called and the algorithm ends, that function will also disappear, so to speak, right? Uh, so essentially what they are function objects, anonymous function objects that have maybe certain names that are specified by the compiler. And the nice thing is that maintenance is simple. Just think about maintenance. Many times when we want to use our algorithms, we need to write functions. Our function objects, as we just saw, that are potentially only going to be useful in a very limited context, which is to do something in relation to a particular algorithm. And so it's a lot of work and tedious work to get out of the function that you are defining and to go define another function so that you can come back into your function and continue with your work. And to remove that tediousness, this was something that came about in 2011 with lots of additional features being incorporated in every new release, right? So let's look at function objects in some depth, or lambdas, I should say, in some depth, so that we can kind of explore more complex things. In fact, some of the things that you do in uh, the next assignment can actually be more conveniently implemented using lambdas. So lambdas are pretty much the way to go about doing things, rather than at the expense of function objects. They come down in terms of the popularity. But there are particular scenarios where a function object could come in handy in contrast to a lambda, right? So let's go look at some lambdas. So I have something called lambda 0, probably an introductory one. And why don't we just go look at that so that we have an idea of what it looks like. All right, most of the stuff is boilerplate that you've seen, boilerplate. So now the important thing is that we're no longer going to write these function objects in this outer scope. Whatever we need, we are going to define these anonymous things, function objects or functions or whatever you want to call them, wherever I need them. And that is essentially where, as one of the arguments to one of the standard library algorithms. So let's go look at it one because I can't find one. Okay, so I'm generating values, and what I'm doing here is I'm performing some filtering operation. What does filtering mean? Basically, I have a list of employees. right? I would like to create a filter. A filter essentially, my background is electronics and computer engineering. We study a lot of filters, although I've forgotten all that stuff. But the basic idea here is that you are taking some input and you are studying the input and letting out through the gate as output only certain aspects of the input that satisfy certain constraints, sort of like a low pass filter, high pass filter, and so on. So I would like to filter a collection of odd values from this container, right? And we have filled it with some values. Obviously, there are odd values because 10, 11, 12, 13, 14, 15, there are some odd numbers there. And I would like to filter out, right? I don't want to change the original. I just want to create a new container that contains only the odd stuff. And this is fairly common. You want to iterate through a bunch of enemies and get the ones who are too strong, are too weak, whatever, right? Are too far, are too close, what have you. Too powerful, not so powerful. So these are common things, and the common term we use in programming is filtering. So the copyif is a great algorithm to do that. Why? Because what it does is that it goes through the original range of all the values, and if any one of those values is odd, then it's going to make a copy of those values into another container called odd, right? And odd, I have no idea how many odd values there are. So I'll let the iterator adapter essentially take care of memory allocation and all that other stuff. That is the basic idea. Now I can do the same thing with another container by using what is called a lambda expression, right? It's got this weird syntax. It looks like this. This is called the capture class. And then just like any other function, because remember, these are the sort of inline functions, smart, short, sweet little things that behave like functions that can be implemented without you having to go to some outer scope and define a function and provide access to objects that are in this scope to that guy that is defined elsewhere, right? All of that is annoying, and instead now we have much more locality. In other words, you're writing code where it is of use. And it's so trivial that the idea here is that if you need to do this again, well, it's better to replicate it than actually to store it. And obviously we need to be able to store these things, and we'll look at that potentially in the next class. So you got the capture class, which is the square brackets, then the parameter list, and then the body of the function of the inline function. And this entire enterprise is returning a value which is of type int. And this is called a lambda expression. And you will see that this guy is going to do exactly the same work as this guy, which is also something that we implemented, which is this. Give me a moment. I have these really bad allergies, and that makes my sinus go nuts. It lasts for exactly 1 week, and it started yesterday. So it's all like my head is bloated up because of the sinuses getting pinched. All right. So any questions, guys? So this is a very simple example, and what we need to understand is how is it implemented, and what other things we can do. And I have some examples I can show you, and we'll also kind of continue to extend the material until we get to C++ 17's advances with respect to lambdas on next week, Tuesday. All right, let me show you some of the things we have. So this is a nice little picture because it contains uh, all the important things. So the capture class, some people call it the head. So it's a very easy way to describe um, what's going on. Basically, they are giving you access. You are getting access to things in the outer scope. Okay. And you can do the access by making copies, which is what's happening with A there in that example, or via references, which is what's happening with B. And the arguments are, since this lambda is like a function object, is like a function, is like a function pointer, they're all callable objects. And any callable object must be able to specify a parameter list. And that's exactly what you see there. When I say arguments, what I mean is arguments in the calling environment, and in the lambda environment, these are more correctly parameters. Then we have the body of the function. In 2011, when lambdas were brand new, they weren't brand new for until 2015, right? It took a bunch of years for people to shift beyond 2011. But it's just the body of the function, and I can return. So obviously, whoever's invoking this function inside some algorithm is possibly using the return value to assign to the object that is pointed to by the iterator. And in between the arguments and the body, we can have this optional list, mutable, const expression, then we can have expression attributes. And if the return type is something that cannot be deduced, for example, the compiler will easily deduce that based on the function parameters x and y, both of type int, and supposing a and b, the two things that are being described in the capture clause here are also ints, then the entire expression is int and the compiler will deduce the return to be an int. But the bottom one basically allows you to be explicit. If maybe you don't want it to be int, you want it to be a bool or whatever, you can convert it, right? And then specify the return type not to no longer be an int. So we'll go through these as in short order. Give me one moment. Okay. All right, guys, some more examples. So I have a vector and I'm counting using, you can see here the simplest form of count, which is specify a value. I think this came up in the midterm, and this is as simple as it gets. And we are going through the range and determining counting how many other values are equal into 3, and apparently in this case, as you can see, it's exactly 1. Now notice the lambda can actually be defined, and this particular object can actually represent the lambda. And anywhere, anytime you want to invoke this particular lambda, well, basically what this is going to become is a callable object. All it requires is the function call operator, right? So you can call it all by itself. You don't need to pass the object to the algorithm. Now, what is the type? The types are pretty confusing and complex. So for the first time, I'm going to go ahead and generalize everything to be of type auto, right? Auto generally works. So if many of you are simply using it, then we do need to study template argument deduction. Because if your code is completely littered with autos, and sometimes you want to know the type or the compiler is unable to compile for whatever reason, then one can get lost. So I think I prefer not being in that situation. So I try to avoid the use of auto. Not that there is anything wrong with it. It's just me, right? Because I spend so much of time without auto. All auto does is remind me of the C auto, right? So you can actually specify the type, but we're not interested, so we won't do that. Instead, we'll use the keyword auto. Sorry. And what am I doing here, guys? I am, as you can see, um, passing a copy of whatever this object is to the algorithm. It's a callable object. And what the object is going to do is it's going to use the function call operator to essentially pass a specific value and return a result. And that is really all there is. Any questions? Let's take a moment to kind of one more example, I guess. Yeah, generally speaking, if you are within a function, feel the need to call this particular callable multiple times, then that is how you go about. Otherwise, you simply write the lambda in line. So the compiler will check for syntax. If everything works, then it's going to convert that particular entity that you see there into a object, into a function object. And I'll kind of explain that in a moment. But as simple as that, right? It's actually a lot more pleasure to write function objects than it is to write no lambdas. It's far more convenient to write lambdas than it is to write function objects. So once you begin on lambdas, it's very rare that you're going to come back and use these function objects. Okay. Um, a particular name is that these are stateless. Notice that they don't retain any state. What's happening here? Well, is the algorithm is going to iterate through each element. Each element's value is being supplied to this lambda expression by value. And I'm checking if that particular value is greater than 3. And if it is, then we are done because we are returning true. And not done in that sense, we are just keeping track and incrementing some other variable. So this is nothing but each one of the elements in the container in turn. So what do we do with this capture clause? Well, I have a bunch of examples and some more examples to show what's going on. There are many confusing ways initially to kind of look at all of this. So the first one is what I showed you. We are taking the outer scope variable A and we are getting it passed by value. While B, on the other hand, is also some outer scope variable, but it is being, reference. It's being passed by reference. That's kind of what I said, what I need to say. There's nothing here. We care about the outer scope, right? Or maybe there are no variables defined in that scope. Then this syntax basically says everything. Now, some people worry that if your outer scope has lots of variables, then you're passing by reference all of those variables. That's not the case. My understanding is that only those that are being used by you, right? So there may be 100 variables in the outer scope, but you're using only 5. So rather than list them one after the other, some people recommend doing this. Others think it's a very poor habit, and the programmer is discouraged from doing that. And then again, passing by value, that can get expensive, except that it's only the values that are being used that get actually physically copied. Now, this is interesting. This obviously refers to this pointer. And where do we see at this pointer? Well, we see it in a class-based object. If in that class-based object, you have a member function that is using a lambda, then you may end up with syntax that will require you to get access to the objects defined in the scope of the this object. Maybe you want access to some data, whatever. You can do that using this. So this, everybody is going to be passed by value except this. And then similarly for this guy. Everything is passed by value except B, which is passed by reference. So once you get the hang of it, I think it should be all right. So here's an example, guys. In one case, I'm passing by value. In the other case, I'm passing by reference. Obviously, there's no particular reason why I pass by reference because we're not doing anything, but simply to demonstrate. So I want now to kind of have our focus shift a little bit to, how exactly, what is under the hood of these lambda expressions. So let's take a moment to kind of look through what's going on. Right? I want you to kind of spend a minute or two. These are some of the questions that may show up, right? In the final, can you guys take a piece of paper and pencil and say what exactly is the last line, right? Is asking what is the value that is going to be stored in that particular variable. And because I want you to understand what happens when you capture by reference or capture by value. All right, so we have a vector container vi, nothing special there. We have a variable x, and then we have a lambda called is above, which looks fairly trivial too. It takes at the point of its definition. At the point of its definition, it is capturing by value. Okay, that is quite important. It's capturing by value the current value associated with x. So by value, so you are getting 3. And this entire lambda expression is going to be converted into some class-based object, okay, that is not visible to us. And so when you come back later after the definition of the lambda expression, notice that I'm changing the value associated with the variable x from 3 to 4. And then I invoke the COUNTIF algorithm, which goes through the entire range, half open range, and checks which one of these values in the container are greater than 3 or greater than 4. That's the only thing left to answer, guys. Greater than 3 or greater than 4. Yeah, 3 because you captured by value from the outer scope. Once you capture, as I'll show in the next slide, the compiler, like I said, is converting this into some sort of a function object, right? And once that function object has been defined, once the value has been captured, when you capture by value, you don't really care about anything other than the value 3. So whatever local variables you need are already initialized with the value 3, and they don't have any particular access to to the outer variables anymore. But what I've done here is that I've updated x, and then I call the countf. Since it's 3 is above is going to get 1. 1 is greater than 3, no. 2 is greater than 3. 3 is greater than 3, no. 4, 5, 6. So we get this variable to contain the value 3. Does everybody agree with me? So
Yes.
is 3. Well, here I'm capturing a reference. So if you have ever defined classes where the data members are references, then it becomes obvious that it doesn't matter. As long as that particular referenced object is in scope, you're good. And obviously, as I just mentioned, the big thing for you is to make sure that that object that you are referencing is always going to be in scope. If it isn't, then you have a problem because the behavior is going to be undefined, right? You're referencing something that doesn't exist. And that is what's going on here. So the values here would be greater than 4. So it would only be 2, 5, and 6. Make sense, everybody?
Yes.
Okay. Right. So I wanted to make sure everybody understands, because at a certain point, lambdas will continue to get more complex, and sometimes you need to have the background, right, of how they actually get built in memory. And so the picture on the left shows the lambda from before, where we are capturing or passing by value. And notice the definition, right? So this is a pseudo class definition. Is it going to look exactly this way? I hope so, unless I don't know something. And the only difference is that all these names are fake, right? Who knows what those names would be? So what's going on here? The compiler looks at this, everything is good, so it converts it to this. And what exactly is going on there? Well, you have a capture by value. So you need a constructor. Make sense? And once you capture by value, you've created a type that might be different than other lambdas that may behave exactly the same way, but don't capture by anything at all. They're stateless. So therefore, they don't have this data member. And therefore, their type is going to be different from your type. And they have the overloaded function call operator. As you can see, it gets the value y. And that's really all there is. And then the compiler kind of takes this definition and instantiates an object of type isabelle, or this guy, and temporarily instantiates an object, and to make sure that this constructor gets invoked. To get this to do something proper, I have to do this, because you have to trigger this particular call so that this data member is going to be initialized. That's really all there is. So every time you see a simple lambda expression, remember in the background there is all of the stuff that goes on. Any questions, guys? All right, let me complete the next slide because my eyes are just going nuts. So I'm this close to the end of the class. Okay, by reference, obviously, we need to have a constructor. And since we are making references, we need to have a data member that is also by reference. And notice that the construction proceeds that way. We are passing by reference and oh, did I make a typo here? Yes, that's a typo. And so not much difference except that you have to be really, really careful. And this is strongly something that you shouldn't be really be doing are this. I'll tell you why, right? Take a moment to look at this code. You're passing by reference. What if the guy that you're referencing, goes out of scope? Big problems for you. But when you capture by value, it doesn't really matter what happens to X, as we just noticed. It got updated to 4, but nothing bad happened to you. So I think it's not a good idea. There's this syntax wasn't there in 2011. It's 14 or 17, I'm not sure. But you can now actually initialize sort of variables in the capture list. And what's happening here is that when you make a call to this callable lambda, that's redundant. I just say lambda or I just say callable. What's happening is that you are iterating through this container. That is the syntax for numbers to be initialized with this stuff and to have this particular type. I presume that somewhere here, invisible to us, there is some auto declaration, or maybe not. And I'm happily iterating in my function body. All right, no parameters being sent. This is the body of the function, and I'm iterating and printing the values to standard output. And I thought I would show you how the class gets constructed because it's quite interesting, right? We are not just talking about passing by value or passing by reference. We're actually defining a brand new object. So obviously, if numbers is of this particular type, you need to have in that anonymous function object some private data member that can store exactly similar stuff, which is what I have here. Then we need a constructor that, and this is notice a default constructor because this is taking place as part of the initialization process. So this is going to be specific. This is going to be specified as this is going to be specified as the initializer, and the rest is pretty simple and straightforward. Obviously, this function embeds the more popular things from the overload. All right, so same idea. I hope you're getting a deeper sense. And then you can also pass smart pointers. So here we need to be able to copy a unique pointer, and the only way to do that is not to be able to copy, but instead to move. So I could do that. This is a new variable that is going to steal the stuff that is stored here. Okay. I can define an initializer or a reference object that is initialized to be a reference to this guy. So lots of different things, but I think I've generally covered most of the things that you're going to come across. All right, I'll talk about mutate and all the other stuff, generic, composition. There's a whole bunch of stuff, generic, and then variadic templates, all that stuff is going to be next week. All right, guys. Any questions?
I don't have questions.
All right. It's possible that don't get hassled, I might add, just so that if somebody has some time, I don't want you guys to be struggling at the end. So I'll add assignments, not too many, but enough after the first submission so that you can add another one, right? And probably the new one is going to be related to the topics that we are covering today and next week. So some of the things may not make much sense to you. In that case, don't worry, we'll cover them. But if some of you want to do the research, get going, that's okay too. All right. If there are no questions, I'll see you guys next week. Have a good holiday.
Thank you.
Yeah, you're very welcome. Thank you.
Hey, thanks, Professor.
Welcome.